Welcome friends, Igor is here, and in this video we will learn that linear transformations can be performed by matrix multiplication. In this lesson we will observe that multiplication by fixed matrix results in a linear transformation between the vector spaces of column vectors, prove that every linear transformation between the vector spaces of column vectors can be represented as multiplication by fixed matrix, and learn how to find matrix representations of linear transformations between the vector spaces of column vectors. Let's get started. We begin by looking at a motivating example. Let's take this 3x4 matrix A, and we can define a function p from C4 to C3 as multiplication by this fixed matrix A. The matrix A has size 3x4, therefore the vector x must be a column vector of size 4, and the resulting matrix vector product is a column vector of size 3. We can describe this function explicitly by using the definition of the matrix vector product. This is a linear combination of the columns of the matrix, where the scalars are the entries in the column vector. We can perform the scalar multiplications of the column vectors, and we can add them up. This gives an explicit definition of the function p on any input vector x. What we are going to understand next is that this function is in fact a linear transformation. I will not perform a direct computation in this specific example, rather I will prove that this is always true. Multiplication by fixed matrix on the left is a linear transformation between the vector spaces of column vectors. This is a simple consequence of the properties of matrix multiplication. Let's take two arbitrary vectors x and y in Cn. Then the value of t on x plus y is given by the matrix vector product. But we know that matrix multiplication distributes over addition. And this is t of x plus t of y. This computation shows that this function t respects vector addition. Next, let's look at the value of t on a scalar multiple of a vector x. It is given by this matrix vector product, and from the properties of matrix multiplication we know that we can take the scalar alpha and move it in front. The matrix vector product is the same as t of x, and we have shown that the function t respects scalar multiplication. Therefore, the function t is indeed a linear transformation. So, this result shows that it is easy to construct linear transformations from column vectors to column vectors. All you have to do is fix one matrix of an appropriate size. But in fact, every linear transformation between vector spaces of column vectors has this form. Every such linear transformation is actually multiplication by a fixed matrix A. We will call this matrix A the matrix representation of the linear transformation T. And the proof of this theorem is going to be constructive. I am going to show you how to construct this matrix A that does the trick. So we have this linear transformation from Cn to Cm. We are going to take a basis of the domain Cn. For example, let's take a well-known basis of Cn, which consists of standard unit vectors. Then we are going to compute the values of the linear transformation T on each of these vectors. These values are vectors in the codomain Cm, and we are going to call them Ai. Now we are going to use these column vectors from Cm to construct a matrix A. Notice that A is an m by n matrix because it has n columns, and each column is a vector from Cm, therefore it has m components. I will now prove that to apply a linear transformation T to a vector x is the same as to multiply this vector x by the matrix A on the left. First, let's decompose the vector x into a linear combination of the basis vectors. Because they are the standard unit vectors, this is easy to do. Next, a linear transformation respects vector addition. Also, it respects scalar multiplication. But now let's recall the definition of the vectors AI. The last step is to recognize the last expression as the definition of the matrix vector product. So we have proved that the linear transformation T is the same as multiplication by fixed matrix A on the left. Moreover, we have explicitly constructed this matrix. The columns of this matrix are the values of the linear transformation on the standard unit vectors. Let's apply this to an example. We have a linear transformation S from C3 to C4. By what we just proved, it should be representable as multiplication by fixed matrix. We construct this fixed matrix column by column, where the first column is the value of the linear transformation on the first standard unit vector from the domain C3. The second column is the value of S on the second standard unit vector, and so on. But notice how easy it is to compute the values of this linear transformation on standard unit vectors. Do you see the pattern? For the first standard unit vector value, you pick up the coefficients that come with x1. For the second one, you pick up the coefficients that come with x2. For the third one, you pick up coefficients that come with x3. Once we have computed these values, we put these columns together into the matrix C, and by what we just proved, the linear transformation S is the same as multiplication on the left by this matrix C. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will learn that a linear transformation can be defined uniquely by prescribing arbitrary values on a basis. I will see you later.